This is exciting. I think I was here 3 years ago in the same stage, speaking about serverless in general. And today we are going to talk about serverless inferencing and give you our point of view from the infrastructure side. So I'm Jan. As Anne-Claire said earlier, I'm the co-founder and CEO of a company called Koyeb. I've been building cloud infrastructure for 13 years now. Quite a bit of time. I built 2 other companies before. I was part of Outscale at the beginning, did all the launch of Skyway. And today I'm accompanied by Alistair, who joined us with Koyeb.
Hi everyone, I'm Alistair, head of DevRel at Koyeb, and I've been there since the early days, and at Koyeb we're building cloud serverless infrastructure. So we've heard a lot about AI today and in general. Today I'm going to be talking to you about the infrastructure, because what's behind all of this AI? And the answer is infrastructure. So 28%. AI infrastructure represents 28% of all the electricity consumed in data centers, IT power in the United States. And that's a huge number. We're only just getting started. If you look at the projections, analysts estimate that there's going to be an increase, 500% increase in data center power capacity for AI alone over the next 4 years. These numbers are huge. Like, we had a hard time believing it when we saw them for the first time. The fact is that that's the reality. Things are already in motion. This is happening. If you look at just the cloud industry alone in the United States, it's consuming 5% of all the energy produced by the United States. So one of the problems, or like the big problem right now, is that AI infrastructure is widely inefficient. And then the question is, why is that? And well, the answer is, frankly, the software isn't where it should be. AI infrastructure goes massively underused because lack of capable software. We see it a lot at Koyeb. We have users and customers, startups, scale-ups that are already spending over hundreds of thousands, $1 million on AI infrastructure alone, and they're looking to optimize their AI infrastructure and to make their deployments more efficient. Before going any further, I think it helps to talk about what exactly we're talking about. There's a lot of different shapes to AI infrastructure, and this is where it's going to get a little interactive. Just by a show of hands, who in here is training large models? Anyone doing large training? Yeah? Okay, a couple hands. Makes sense, NVIDIA. Yeah, because reality is there's only a couple dozens of companies doing this worldwide. The kind of infrastructure you need to be doing this is high-performance clusters, high-speed interconnects. We've seen now clusters of 100,000 GPUs to train the kind of foundational models that we all are familiar with today and using today. All right, now on to fine-tuning and small training. Show of hands, who's doing fine-tuning or some small training? This makes sense. Seeing more hands here makes sense, because we estimate that companies that are advanced in AI will be doing fine-tuning and small training. The infrastructure you need here is much less intensive. You might need like 1 to 8 GPUs, maybe some small or like several machines for some small clusters, and that's about it. Last but not least, the famous inferencing. Who in here is doing inferencing? Show of hands. Yeah, that makes sense. That makes a lot of sense, because in the short term, we're all going to be doing inferencing. Show of hands, who's doing real-time inferencing? Yeah, okay, even less so, but all the same. This kind of workload, like what you need, we're all going to be doing this, whether it's on device or via an API. Usually it fits onto like 1 GPU. Maybe the larger models, you might need a couple GPUs, but that's about it. And when it comes to power usage in AI infrastructure, right now we're at a stage where most of the usage is happening under the large training today. But we're going to be seeing a shift towards more and more people doing inference, which means that there's going to be more usage going forward for inferencing and more power being needed there. So what can we do with the state of AI infrastructure and the fact that there's underused GPUs? Like, how can we improve this? The thing is that you can't split a GPU. Well, the thing is you actually don't want to, because if you're doing inferencing with a GPU, you really want to harness the full processing capacity of that GPU for your inference workload. And so you're going to have to use different strategies. So in terms of optimizing, there's two sides to optimizing in this case. There's the hardware elements, and then there are the software elements. For our talk, we're really going to be focusing specifically on that real-time serverless inferencing, which is different than asynchronous serverless inferencing, because in that case, you don't have the high-performance constraints. You can wait a few minutes, even hours, to process those requests, whereas with real-time serverless inferencing, there's someone waiting at the other side of that device on a screen, and they need a response in a second. And so in these cases, we're talking about low latency, high performance infrastructure that you don't want to have to manage, hence serverless. And so that's where we'd come in talking about what we're doing at Koyeb.
Yeah, I mean, so what we're doing at Koyeb is we are building a global serverless platform for high performance fine-tuning and inferencing. That's not the only thing we cover, but today we are going to focus on the inferencing use case, as our listener was saying, and actually I'm going to do a live demo, if the demo gods are with me. Okay. Can I get this mic to work? No. Okay, awesome. So that's perfect. Sorry, guys, we're getting ready. So what we're going to do right now is we are going to deploy a private auto-scaling serverless inference endpoint, which is going to run a llama 3.18 billion parameter, which I think was mentioned earlier by the Miracle team. And we are going to see actually what's happening. So we are going to go to koyeb.com/deploy/vllm. Hopefully it's big enough. Looks like it's big enough. And we're going to hit deploy on this ready-to-use image. And what we have here is we're basically seeing that we are using a Docker container, which embeds VLLM. It's actually running on a GPU with 20 GB of VRAM. We could change the GPU. For today, we don't need to. We can change the scaling parameters. So we'll say we want to auto-scale up to 3 instances. We'll define the criteria. We're going to say it's going to scale up if we get more than 3 requests on average per second. And we are going to hit deploy. So what we see now is our deployment is happening. It's going to create like the first instance. And we are going to have a public URL where we can make our queries with an OpenAI compatible API. This should take about 1 minute or 30 seconds maybe. And while this is happening, I'm going to use one which I already deployed. So we see that it's actually running. But I had a backup. This one is actually running on an A100 GPU, so more memory because it's a 8 billion parameter model, and it would be actually, the other one was actually too small to fit the full model. And we see that it's actually currently running only 1 instance. So we are going to generate some load. We are going to connect to a remote machine, and we are going to do some load testing together. So I have a command line here, and it's actually using the embedded VLLM benchmark. It's going to generate 3,000 prompts. And on the LLM-in-production.koyeb.app URL, where our A100 GPU is right now running. So if I go back here, I see that the queries are starting to come in. We're on the same web service. And what we're here doing is we're observing requests every constantly, and every 15 seconds, we actually take a decision based on the traffic from the last minute. And so we are going to see more instances pop up here in about a couple of seconds. And here they are. Ta-da! And that's it for the demo. So basically, what we see is that it's spawning several machines depending on traffic. And the reason why we create them we take a decision only every 15 seconds is to avoid the cold start problem, basically. So,
yeah, gonna jump back to how can we answer, or like what's going on behind the scenes and how can we optimize AI infrastructure. Like we said earlier, there's two sides to this problem to address. There's the hardware and then there's the software. So to dive into the hardware, surprise, surprise, the landscape is NVIDIA.
we love you.
We love you. There is a bit of a problem with the fact that there's only one vendor on the market. It's not typical that we like to only see one option. And luckily, things are changing. Diversity is coming, innovation is coming. So much, the boundaries are really getting pushed. More vendors are going to come to market with next generation chips. And these new next generation chips are being designed with efficiency in mind and with inferencing in mind specifically. So that's very exciting. With these new chips, you're going to see accelerators with diverse options for memory. So things between 12 gigabytes in memory to up to 256 gigabytes of memory. So if you're running a smaller model, that means you can use a chip that's more adapted to your workload. If you look at the largest models today, that means you'll be able to fit them onto two GPUs maybe, and that's really exciting. These new chips are also going to be made with different speeds for different purposes. Some of them might be slower, we can say. I mean, I say slow, and I mean like they'll be processing data at like 100 gigabytes per second, compared to other chips which will be designed to process up to like terabytes of data per second. And then also in terms of like infrastructure, like they're going to have different architectures and they're going to have different power requirements. Some of them are only going to need a few dozens of watts versus others are going to need up to 600 watts. And all of this means there's going to be an increase in performance and a reduction in costs. So the price you're seeing today to run large models in the future, or to run small models, is what you're going to be able to pay moving forward to run larger models. So that's very exciting. And I will give it back to Jan to address the software optimizations.
Excellent. Here we are. So on the software side, it's actually like one key part of the problem. Like Alexander was explaining that we will get way more diversity on the hardware side, but the hardware is technically worthless if you don't have the right software. And a lot of the performance bottlenecks are actually coming from the software side. So there are two key sides. One is inference servers. The second one is how you deal with distributed inference. At the beginning of the talk, Alistair mentioned we need to scale horizontally to handle more requests. And that's where actually we're getting to the problem of how to deal with it. So on the inference server side, the main subject when you want to bring new hardware to market is how do you optimize compatibility. NVIDIA has built a tremendous software ecosystem. They have probably one of the best inference server right now. And we're starting to see alternatives which are emerging to optimize performance, like VLLM, which is actually quite a recent project. I think it's 2 years old maybe or something like this. And every single new hardware vendor needs to build the software to work with these chips. And technically, if you look at this company, they are hardware manufacturers, but they all have huge software teams. So if we look now at what I showed earlier, the distributed inference problem, we need actually the infrastructure to automatically adapt to demand. There are two key here. Like one is like scaling from 0 to 1, which is a process per se, and auto scaling. And the question we're looking at is how fast can we boot an inference server? The reason why we only take a decision every 15 seconds and not per request is because it takes time to create a new instance to process requests. And the technical problem behind it is how fast you can go from a registry to having the model run by the inference server. Behind the scene, when you do this, you have potentially hundreds of gigabytes to transfer and load before you serve a single request. So the call boot can actually take several minutes from 0. You need to transfer all of this data over the wire. And this is typically a remote store which needs to go potentially through the internet. Typically, it's maybe an object store. You have another key thing which might take a lot of time. If you're really going from 0, you need to start the physical machine. This with the accelerator, if it's a large machine with a lot of memory, it's going to also take several minutes. And then you need to boot up your virtualization layer if you're using one, and the inference server. So luckily, on the two first problems, we do have solutions that are implemented in the industries. For the bare metal server, you can preemptively start some of them. For the transfer over internet, you typically use caching, it's a typical infrastructure problem. But then we're still stuck with one key problem, which is the time it takes to boot the inference server. And this is what is going to take you still several minutes. So if you look at this, basically the typical optimization we're looking at is then memory optimization. There are two different kinds of memory optimization. One is model hot swap to avoid having to completely start from scratch. Or you can do memory snapshots. And that's actually the approach we're looking at because it actually works independently, whatever the context, from an infrastructure perspective. And this is actually the technique we use on CPUs. On CPU, when we do restore from memory, it takes between 100 and 200 milliseconds to cold start a workload. And so what we need actually from as an industry to reduce the cold start time is to have optimized model snapshots, which are actually technically the same layering that you have in the accelerator card memory, and copy them at line rates directly to the accelerator card. If we manage to do this, actually the wires and everything behind it, on a typical new generation machine, you can copy 500 gigabytes per second. So if we have a 1 terabyte model, it's only 2 seconds. Today, this is not widely available in production. There are actually some teams working on it. Typically, there is an open pull request on VLM to solve this. And we expect to see this happening in the short term. To sum up, low latency inference actually requires optimization at all layers. We have two key takes. One is today, as long as we don't have all this optimization implemented as an industry, applications tend to need to provide hints to infrastructure. So typically, it's going to make a first request when a customer lands on your app and might need to do real-time inferencing so that you avoid some of the cold starts while we solve the cold start problem.
Yeah, and then the other take that we have is that you're going to see a huge increase in efficiency and a big improvement for price to performance moving forward. Which is exciting because that means that the limitations aren't going to be the infrastructure, which is good news for anyone building AI applications next year and onward. And if you found anything that we were talking about interesting, we're hiring and we'd love to talk to you. We also, if you have any questions about any of this, we're super happy to talk about it. And we also are providing $200 in credits. That way you can get started and simplify your deployments in AI infrastructure. Thank you.